Micro XRF. First we have to prepare the sample. Sample preparation involves cutting or polishing or mounting the sample onto a suitable substrate. The sample should be flat and securely mounted to ensure accurate analysis. There are non-destructive samples which should not be touched. Such kind of samples can also be analyzed here. The requirement of flat sample is to gather the focused beam on a particular surface. In case if it is not flat, the focusing could be difficult. Then turn on the micro XRF instrument and allow it to stabilize. Configure the instrument settings such as beam energy, beam size, and measurement parameters based on the sample type and desired analysis. Then position the sample on the sample stage and place it under the X-ray beam. Then close the door. Either you can close it from the software or else you can close it from the machine, the white button here. Then press vacuum. It will make the chamber vacuum. During the vacuuming process, the vacuum light will keep on blinking until the required vacuum is reached. Then position the sample under X-ray beam by adjusting the stage or sample holder. This can be done by the software. By using all these tools, you can move it in all four directions, or you can make it up or down, and also you can focus it. So by adjusting it to right or left, up or down, so these tools are available to adjust the sample so that it may under the focus. The focus can either be 10 into or 100 into. First we will go for 10 into, and then for more fine image we will go for 100 into magnification. Here you have lighting control. So the first one is lighting for sample and the second one is lighting of the chamber. You can increase or decrease the lighting based on these two tools. By selecting a tool and draw an arrow mark on the particular direction, you can move the stage. So by these steps, align the sample to ensure that the area of interest is within the field of view and properly focused. You can select the borders here. So you find the red point there and bring it to the downmost and upmost positions so that it may fix that area should be the scanning area. So what we do, we go for mosaic and then we will capture that particular red symbol within a cage. So we will place it at the bottommost area point as well as the topmost point. Similar thing we will do for the area correction also. We will click the area and we will click mosaic. So the area, an area would be appear on the screen. So we can place the area on the region which is in our interest to scan. So if it is only one sample, we can go for that particular sample. If you are going to scan more than one sample, we can scan like that also. So here you can see both the samples are captured in one area, and once you select the area, you can check how much of time it's going to take. So you just can click the symbol near to the acquire, which will show how much of time is left. So time in pixels 5 millimeter per second. That's how it's going to scan, and the time taken will be 5 minutes for this particular region. By changing the micrometer distance, the time taken for the scanning will also be changed. So this micrometer distance means each point which is going to be scanned. So each point in 50 micron distance will be scanned. So this distance you can change. You can go for 30, 40 or 100, depends on your sample dimensions. So the measure points which are shown as X and Y are the points uppermost and lowermost. And the analytical area which is showing left millimeter, top millimeter, so all these points are being shown here. And then you can name your sample. Then you press acquire. So now the scanning is started. So here you can see from the right top corner map running. So this box shows how much of time remaining. It will show like 16 minutes or 17 minutes how much of time remaining. And similarly on the top you can see the vacuum. So vacuum state is 2 millibar, and also the other parameters also you can see the energy, these kind of things, the distance, XYZ length. This distance you can see which tube is being used, rhodium tube, RH, you can see. It is necessary to check the spectrum. Click on the spectrum and to check whether the spectrum is appearing on the screen, because maybe in case if you don't select the particular area, the scanning will be happening, the time will be running, but you will not obtain a spectrum. So while the experiment is being done, it's better you click on the spectrum and to check whether the spectrum is being generated. Moving left or right includes Control plus left or right keys. Adjusting the sample up or down is Shift plus up or down keys. Either after finishing the scan or while the scan is on progress, you can select the elements. So you click the icon which is like the periodic table. So the periodic table will be appearing on your screen. You go for Finder, which will find what are the elements which are present in your sample. After selecting Finder, on each peak when you press your mouse, it will show which element is present over there. So every time you click on your graph, the element which will be shown on your graph. At the same time, on the bottom, when the number of elements are keep on increasing, say for example when you click first time, sulfur appeared, then you click for the next time, calcium appeared, then you click for the third time, say for example titanium appeared. So in that case, in the bottom, each element would be keep on adding. So in that case, once the scanning is finished, when you click on any of these particular element, which will show the distribution of it in the sample. So if you click calcium on the bottom, that will show what are the areas calcium present on your sample. If you click strontium, that will show what are the areas strontium present in your sample. So by clicking it, you can see which element is being used, what's the maximum power, what's the voltage, what's the current. This whole data you can see by clicking it. So here in my case, it's 50 kV voltage, 600 microampere current and 30 watt power. maybe for rock samples, most of the areas would be silica, and there would be some places where Fe is present. So depend on your sample and the distribution of elements would take place. So once you selected your elements, you can see from the bottom which elements present on which areas by different colors. You can select all elements at once to see the complete distribution, or you can select one by one to see the particular distribution of each element on the sample. If it is a homogeneous mixture of sample, then we will see all the elements present like everywhere throughout the sample. But in case if it is not, then particular elements will present on different areas. If you feel that that element should not be there, then you can remove it as well. So here I am removing titanium because titanium should not present in my sample. So it could be because of from the double side tape. So that's why I remove titanium here. So this is how we remove titanium. We click on the element and then we'll go for remove. Let's see how to determine whether the element is present on the sample or on the double side tape. So if the element is present on the sample, it will appear, the color will appear only on the surface of the sample. If it is present on the double side tape, you can see throughout the rectangle area of the double side tape, you can see the color. So here in case of calcium, sulfur, titanium, they all are present on the double side tape because the color appear on the rectangle area of the double side tape. But in case of Fe, Mn, these elements, they are appearing only on the irregular shape of the sample, the color, right? At the later part of the video, we'll see a sample which does not have any double side tape on it. So we'll see the distribution of elements on that particular sample. And if the surface of the sample is not flat, this kind of problem you will face. So you see here the top of the sample, it is not being scanned because no color appearing on it. So which means that there are no any elements, but there cannot be any sample that without any elements, right? So in that case, we have problem with the sample. If it is not flat, the focus will not be proper and the reflection will not be proper. So this is why we need a flat sample for this experiment. Within the complete sample also, you can select a particular region of your interest. It can be a square or rectangle or circle, depends on your need. So on the right bottom side, there are tools to select different shapes. So go to objects, and on each tool you can see rectangle tool, circular tool, freehand tool. There are different tools. So you can select one of the tool and you can draw the desired shape on the sample. After drawing the shape on your sample, you can move it as well, and then you name it into a different name, maybe for that particular area a different name. So as many regions you select, you can name them into different names, and later you can compare. So here this video shows that this particular region shows that how the scanning is being done. So this is the movement of the scanning for every 30 micrometer. So every 30 micrometer it's capturing a point. So that's how we find it. And here you see, after scanning each layer, the scanning is now being finished. You can see it from the top time also. Now it's 2 minutes, 2 and 40 minutes left. Here is another sample. So I will select another region here and I will give a different name for that. This can be compared later. If it is different pieces of single sample, you can compare the distribution of elements, or even if it is different samples itself, you can still compare, depending on your need. All these data would be generated in separate files. By clicking your results and then click on spectrum on the top right corner, you can generate the spectrum. So here is a quantification of the elements which are present and their percentage wise and weight wise data. So this spectrum will include whichever the elements you have already identified. So you select the element, go to spectrum, and then quantify. Then you can select the elements whichever you want. So this is the spectrum you obtain for the sample you present. A sample which does not have any double side tape on it. So we'll see the distribution of elements. So here is an example of a homogeneous substance. So here you can see when you click on each element, it's almost distributed throughout the sample. Then you can create a folder for yourself and can save all the results you obtained. So how do we save? You click the icon which is above the icon of the periodic table, the save icon, and then you can select whichever the folder you need on whichever the location and create a folder for you, your name, and all these things would be saved on that particular folder. After checking, you can cross check as like usual save process. You go to your folder and check whether it's all saved. There you can see all the data is saved, and later you can extract into different files of the spectrum diagrams, the Excel sheet of the values. These all you can extract. And then when you click results, you can see what are the elements present, their atomic number, their mass available like in weight percentage, normalized weight percentage. These all you can see. So either by ticking or not ticking the quantification boxes, you can select whichever the parameters you need. If you don't need, say for example, stoichiometric concentration, you just remove it by remove the tick on that. If you need the net sum, then you tick on that, you will have the net sum. Why this is homogeneous? Because you can here see the red, green, blue, ash and all colors are distributed throughout the sample. So each of this color recognizing for each element. Say for example, red is Fe, green is calcium, and so on. So since these colors are distributed throughout the sample, this is a kind of homogeneous sample. Why different colors are being taken by different elements? It's because when you see the right hand side, you can see the color code. So if it is higher amount, then around more than 70%, it will show in red color. If it is around 50%, it will show in brown color. So it depends on how much is the distribution. If it is very low, around 20-25%, it will show in blue color, right? So this is how the color code should be interpreted. We can also save different maps of each element. And here in the spectrum, if you feel any element should not be there, or it's an odd element to be present here, you can remove it as well. So you can delete it. How to decide an element should present or should not present? So usually for this machine, to obtain a good results, what will happen if the element whichever is being identified is before rhodium in the periodic table, we will have minimum 2 peaks side by side. Here see for example, we have 2 green peaks side by side, and then we have 2 red peaks side by side. So for the elements which are before rhodium in the periodic table, so the green one is calcium and the red one is Fe, iron. Okay, we will have 2 peaks side by side. In case if it detects the elements which are after rhodium, right, so there will be usually 3 peaks will occur side by side. Okay, so this is a usual situation in this machine to obtain a good spectrum or good results or confident results. In case if only one peak is appearing somewhere and then there's no peak on that element, usually we will not consider that as an element present over there. Okay, along with all the elements present on your sample, we will get a peak for rhodium also, RH. So this is because the tube being used to emit X-rays is rhodium tube here. Micro X-ray fluorescence spectroscopy is a technique used for elemental analysis of materials. It operates based on the principle of X-ray excitation and subsequent emission of characteristic X-rays from the sample. Let's see how does it function. The sample is irradiated with the focused X-ray beam. The X-rays have sufficient energy to dislodge the inner shell electrons from the atoms in the sample. When an inner shell electron is removed, an electron from an outer shell fills the vacant position, resulting in the emission of X-ray fluorescence radiation. This emitted X-ray radiation has a characteristic energy that is specified to the element from which it is originated. The emitted X-rays are detected using an X-ray detector, typically a solid-state detector or a gas proportional counter. The detector records the intensity and energy of the X-rays. The detected X-ray spectrum is analyzed to identify and quantify the elements present in the sample. Each element has characteristic X-ray energies, so by analyzing the energies of the emitted X-rays, the elemental composition of the sample can be determined. In micro-XRF, the X-ray beam is rastered across the sample, generating a two-dimensional map of X-ray intensities for different elements. This allows for elemental mapping, providing us spatial information about the distribution of elements within the sample. The X-ray intensities can be compared to known standards or calibration curves to quantify the concentration of elements in the sample. Then activate the X-ray source to generate the X-ray beam. The beam is directed onto the sample and the X-rays interact with the sample's surface, causing the emission of characteristic X-rays. Capture the emitted characteristic X-rays using an X-ray detector such as an energy dissipative detector EDX. The detector collects and measures the energies and intensities of the emitted X-rays. Then start the data acquisition process to record the X-ray spectra emitted from the sample. This process involves scanning the X-ray beam across the desired area of the sample and acquiring spectra at each position. Then interpret the results by identifying the elements present in the sample, determining their concentrations and evaluating any spatial distribution patterns. Micro X-ray fluorescence spectroscopy offers the advantage of non-destructive, rapid, and simultaneous analysis of multiple elements in a wide range of materials, including solids, liquids, and powders. It is widely used in various fields such as geology, environmental science, archaeology, art, and material science for elemental analysis and mapping of samples. Usually, the X-ray fluorescence spectroscopy detects samples from carbon until uranium. And more predominantly, micro-XRF is used to find the metals which are present in a particular sample.